a Bondi spherical accretion flow and to introduce on top of it a small amplitude, large density perturbation. As shown by Hernandez and collaborators, the Bondi flow is unstable against this type of perturbation, and the resulting accretion to pulse density gradient dramatically changes the flow morphology into a system with equatorial inflow and a bipolar outflow. This mechanism is intended as a toy model of the inner engine behind accreting black holes associated with ejection phenomena such as AGNs, GRBs, and X-ray binaries. Our purpose is to unveil a very basic hydrodynamical mechanism that might be already present in some of these systems, working alongside more complex processes responsible of wind and jet launching, such as the well-known magnetocentrifugal mechanisms. We have studied this problem using both an analytic model and numerical simulations. This work has been presented in a series of articles exploring the Newtonian regime and the relativistic counterpart for both rotating and non-rotating black holes. The analytic model is based on the general solution for an ultra-relativistic stiff fluid presented by Petri, Shapiro, and Tucholsky. This figure shows our model setup. The flow is being continuously injected from an outer sphere, outer spherical boundary, the injection sphere, where we also fix the flow properties at the equator. As a function of these boundary conditions, the fluid streamlines can be divided between those that accrete onto the central object and those that are redirected as a bipolar outflow. We also measure at the outer boundary the mass injection and ejection rates. This is an example of the resulting accretion flow for a close to maximally rotating curved black hole. The panel on the left shows the density map, and the one on the right the magnitude of the free velocity. The black arrows in both panels show the fluid streamlines. An important characteristic of this analytic solution is that for any combination of the model parameters, the requirement of a regular solution across the black hole event horizon automatically fixes the total mass accretion rate with the corresponding value of the spherical symmetric problem. Given that the ultra-relativistic stiff fluid has a limited applicability in astrophysics, we also studied this same scenario by performing a series of 2D general relativistic hydrodynamical simulations with the numerical code Aztecas. For these simulations, we use a general perfect fluid. We adopt as boundary condition of the injection sphere this density profile that introduces in a simple way the density perturbation behind the choked accretion mechanism. The parameter delta encodes the density contrast between the equator and the poles of the injection sphere. Plotted here is an example of the boundary condition for a density contrast of 10%. We let all of our simulations run until a steady state is reached. The figure shows the time evolution of the mass accretion rate in 4 simulations with 4 different density contrasts and a gamma equals 4/3 polytrope. Note how in all cases, the resulting mass accretion rate is essentially equal to the corresponding Bondi value. The parameter space considered for this project comprises the black hole spin, the density contrast, the adiabatic index, and the fluid state at the equator of the injection sphere. Here I'm showing the resulting steady state accretion flow for the same 4 simulations as before. The figure shows the density map in each case together with the fluid streamlines, here for a density contrast of 0, 0.1, 1, and 10%. Also shown is the resulting mass accretion rate, as well as the outflow to inflow ratio. Note that, as expected, when the density contrast is 0, the Bondi spherical solution is recovered. On the other hand, as soon as the density contrast is larger than 0, the flow morphology changes abruptly into an inflow-outflow configuration. Also note that as the density contrast increases, a larger fraction of the incoming flux is deflected as a bipolar outflow, in this case reaching up to 90%. In this figure, I show a summary of our non-relativistic simulations for different values of density contrasts, as well as adiabatic indices. The horizontal axis corresponds to the mass injection rate crossing the outer boundary of the numerical domain. On the vertical axis, we have the outflow to inflow ratio. The black solid lines shows the analytic prediction of exact choked accretion. In other words, that the total mass accretion rate onto the central object is exactly equal to the Bondi value. As you can see, there's an excellent agreement between this condition and the results of our numerical simulations. This figure is the same as the previous one, but now for the case of the relativistic simulations for a Schwarzschild black hole, we again observe a very good agreement between our numerical data and the choked accretion condition. From these 2 figures, we can see how, as the mass injection rate increases, a larger fraction of the total flux is eventually expelled from the system as an outflow. This provides an appealing simple connection between accretion and ejection flows, not very different to an on and off switch. Whenever the mass injection rate exceeds the corresponding Bondi value, the excess flux is redirected as a bipolar outflow. We have also shown that the choked accretion mechanism can successfully operate with a curved black hole. Since we are neglecting fluid rotation, we found that the flow morphology is essentially independent of the inclination angle between the injection sphere and the black hole spin. On the other hand, the resulting mass accretion rate decreases as the black hole spin increases, as shown in this figure for 3 different adiabatic indices. Note that in curved spacetime, there's no analytic equivalent of the Bondi solution, and this is exactly what motivated us to study this problem in a new paper that should appear on the arXiv tomorrow. And if you are interested, please also take a look to Alejandro's poster on this topic. Finally, some words regarding the astrophysical applicability of the simple toy model that I have presented here. We have found that for this hydrodynamical model to work by itself as a successful ejection mechanism in actual astrophysical scenarios, extremely large temperatures are needed. These kind of conditions, though, might be found in systems associated to hot accretion flows such as Sagittarius A star and other radiative inefficient black holes. We also expect that additional physical ingredients such as the coupling with a radiation field and non-adiabatic effects as magnetic reconnection and internal shocks might alleviate the temperature restriction and thus improve the applicability of choked accretion. In conclusion, the choked accretion model constitutes a simple hydrodynamical ejection mechanism. It represents a transition bridge between spherical accretion and outflow generating systems. A result that comes out naturally from this model is the existence of a flux-limited accretion regime. Based on analytic model and numerical results, we have found that the total mass accretion rate onto the central object is of the order of magnitude of the Bondi value. This means that any excess incoming flux chokes at a gravitational bottleneck and is redirected by the density gradient as a bipolar outflow. This result also offers an appealing simple connection between accretion flows and outflows. Thank you very much for your attention, and I will be happy to take questions now.
Perfect, Emilio, thank you. We indeed have time for a few questions. Sasha?
Yeah, thank you so much for the really interesting talk. I was wondering, how does the amount of outflow depend on the scale separation between the outer boundary and the inner boundary?
Yeah, that's a good question. And actually from our results, the key parameter is the temperature. So the outer boundary is not that important. In our simulations, we don't have direct control on the mass injection rate. The only thing that we can control is the temperature at this outer boundary. So this mass injection rate is something that we measure a posteriori. And as the temperature increases, this mass injection rate increases. So indirectly, we can control this mass injection rate.
So basically, I guess, sorry, to reword my question, you can move the Bondi radius out and in. I imagine if you move the Bondi radius out, there will be more room for the outflow to form. And exactly. So like numerical simulations predict, of course, with rotation for the disk, for the angular momentum. So here I imagine you have zero angular momentum. They predict that the larger is the range of the accretion disk, the less is the amount of gas that reaches the black hole. So do you find something very similar to the simulations with rotation? And if so, then why? If you don't have rotation, how do you? Sure. Why do you feel like there will be a disagreement?
So in this, as I said, this is really just a toy model. So we are thinking that all this system, all this injection sphere fits within the innermost region of an accretion disk. So our assumption is that the fluid that is entering this region has already lost its angular momentum. And that's why in this first approximation, we are neglecting it. So essentially, what you said is completely right. If we take a very large Bondi radius, then this will just grow. But we want this machinery to fit within a toy model for an astrophysical system. So that's why we need to take such extreme large temperatures to make this really, really, really small and fit it within this inner region.
Okay, thank you. I think we have to move to the next presentation. This will be a presentation by Davide Gerosa.
Yep, I'm right here.
Consistent treatment of warped accretion disks surrounding spinning supermassive black holes.
All right. Hope you see the screen and hear me well.
Yes.
Hi all, and thanks Thanks for joining this session. I've been very interested with this conference. I'm kind of an outsider here to the EHT world. I'm really a gravitational wave astronomer, but I hope I can throw some connections with the EHT science. So this work is about studying the structure of warp-distorted accretion disks around supermassive black holes. Right, so as I was saying, I really come from the gravitational wave and the LISA side of things. So when we started this project, we were really motivated by predicting LISA signatures. So what kind of binary should LISA see, and how this evolves. Then as the project proceeded, as often, we ended up doing something slightly different, and this turned out to be a deep dive into distorted accretion disks dealing with nonlinear viscosities and so on, which is what I want to tell you about today. And I'm very interested to see if this is helpful in any way or can connect to EHT kind of efforts. All right. Oh, sorry, this is not working. Right, so the key physical process I'm interested in is the so-called Bardeen-Petterson effect, which sets the alignment between rotating black holes and their accretion disks. So if you have a black hole with a spin in a given direction z, and an and a disk which is misaligned, so angular momentum in a given direction n, forming an angle phi. So what happens is that on a very short timescale, the viscous timescale of the disk, length steering precession from the black hole quickly aligns the inner disk. Not indefinitely, but up to a certain point, up to the point where warps in the disk can efficiently redistribute the angular momentum, which is this critical radius called the Bardeen-Petterson, or the length steering radius or so. Most of the angular momentum, however, resides in the outer disk, which means that on a longer time scale, 5 megayears for typical supermassive black hole and AGN disk parameter, on a longer time scale, the outer disk pulls the black hole towards alignment. So the long-term evolution of the system is that the black hole aligns actually with the outer disk. Now, in my field, in gravitational waves, one of the key issues we've been studying in the past is whether this time is enough. Because if you have two black holes and they will eventually have to merge, you have a finite time to do this alignment process. Right, so this is a rendering of the same setup in SPH simulation by Rebecca Nilon, and as you see, there's the inner disk which is aligned to the in the equatorial plane of the black hole, and then there's a distorted region, and then the outer disk eventually keeps his misalignment. All right, so what we are interested in is devising quick but faithful 1D evolutionary scheme to actually capture this physics, including the behavior of the nonlinearities in the viscosity. So this is a scary slide with the equations. I'll go fast here. So the key system of equations that you want to solve are mass and momentum conservation. So sigma is the mass density, L is the momentum of each ring along the disk, along a radial coordinate big R. And the various terms here indicate, well, terms in nu1, that's the shear viscosity. This is textbook accretion disks. The disk is warped, so you have these terms in nu2. Nu2 is the vertical viscosity of the disk that sets how quickly and how efficiently warps. So the vertical propagation propagates indeed in the disk. We're going to neglect the precession viscosity here because it's well justified. And then the last line, we have the two external torques. J is the spin of the black hole. So this J cross L is what causes the Bardeen-Petterson effect. And we also had a term that takes into account the fact that the black hole can be, as I'm interested for in LISA, in a binary system. So the disk around each black hole is actually perturbed by a black hole companion with momentum L star. So we're interested in solving this set of equations as a boundary value problem where the inner disk is aligned to the black hole and the outer disk maintains a given misalignment. Now, the complication of these system of equations is that the viscosities are actually nonlinear, so they depend on the warp itself. And this is a plot here on how nonlinear they become, and we are talking about an order of magnitude or so. So these are how the dimensionless version of nu1 and nu2 evolve for different warps in the disk. So what we came up with is a new iterative scheme that simultaneously solve for the mass and momentum conservation and the viscosities iteratively. So we start from an unperturbed disk, plug the viscosity into the momentum conservation, and then iteratively solve the two until convergence. So the physical setup here. So for a single black hole, the solution is self-similar and only depends on a single parameter, length steering radius or Bardeen-Petterson radius or so, and this was known before. So that means that a black hole with, a system around a more massive black hole, M, or a more spinning black hole, chi, it would just be self-similar, just scaled up, if that makes sense. When you plugged in a binary system, there's an additional parameter here. And physically, this is, you have an additional radius, which is how it tells you the tidal radius, so it tells you how important the companion is, which very elegantly enters the equation only through a dimensionless number kappa. The bigger it is, the more important the effect of the companion is. So these are some solutions resulting from the iterative boundary value problem. Sigma, the top plot here, that's a mass density. And what's happening here is that compared to an unperturbed disk, this power law here, this warp scenario, they have a strong depletion of surface density right at the warp radius, indeed. In these other three plots, these are the specific the angular momentum per, so for each gas ring along the disk. The Z component is the one that is parallel to the direction of the black hole spin. And as you see, the inner disk, this, equal 1 here, is aligned to the orbital angular momentum. And then there is a warp profile up to the outer disk that maintains a given misalignment that we impose as boundary condition. The X and Y components, indeed, they have to readjust this, they have to connect the inner disk to the outer disk to this through these strong warp profiles. Right, so the key finding of these studies was to identify the existence of we call it critical obliquity, which is regions in the parameter space where these combined viscosity and viscous equations system cannot be solved. And my 1D code just crashes. And we're pretty convinced this is, a real physical effect. Hints of it were reported previously. If you investigate these Tremaine and Davis paper. So in this plot here, I have as a function of kappa. So remember, on the left here, the companion is less important. So this is basically a single black hole. To the right, the companion is more important. So this is more of a binary case. Solutions in the gray regions just don't exist. And here on the left, I have a case close to criticality. So basically, this is the last good solution that I find as I approach this critical obliquity. And what happens is that the surface density of the disk drops to basically 0. And in this bottom panel here, which are the three components of the angular momentum, it's basically two distinct disks, an inner disk aligned with Z, and then an outer disk aligned with X in this case, with basically no mass in between. The next thing that you want to do once you have this warp solution.
Sorry, I need to interrupt you. You're a bit over time already.
Okay, so I'll be very quick. I'll skip this slide. So so we found that through the natural spiral of black hole binaries, black hole disks around them might actually break. And now open questions are actually what happens to the disk at this breaking point. So as you reach this critical obliquity, and for my LISA applications, what happens to the black hole and the black hole spins after that? And we have work in preparation on these topics. Thanks, and sorry for being over time.
No problem. Thank you. We have time for one quick question. Boris?
Yeah. Hi, Davide. I'm wondering, how are you solving for the viscosity? Isn't that something you have to, assume about your system externally? So we use the theory by Gordon Ogilvy, so paper by Ogilvy and Latter 2013 or so. So in their theory, they can compute the viscosity for a fixed warp value. Now, the real problem would be solving things together, but this, as you're saying, is hard. So what we are doing is we alternate between solving the viscous equation at fixed viscosities and then the viscosity for a fixed disk profile, and then iterate between the two until we converge down to some numerical tolerance. But does this viscosity include MHD? No, these are alpha disk effective viscosities.
Okay, it'd be
So we are
curious
dealing
to,
with it is an effective system.
Yeah, it'd be curious to compare this to GRMHD simulations of filter disks, such as the one Sasha's been doing. To see how well
absolutely. Yeah, I love to do this comparison.
Okay, thank you very much. We are going now to move on to the next talk by Dominique Schleicher. Dominique, if you could share your screen.
Yes, I'm about to do so.
Okay. Predictions for the ng-EHT from ADAF-models.
Yeah, everybody can see the screen?
Yes, go ahead. We can hear you well.
Yeah. So this is work that has been, a lot of it has been carried out by Bidisha Bandyopadhyay, who will give another talk later, but she's also here, so we can both answer questions. What we did here, in fact, was trying to make predictions for observing other nearby low luminosity HEN either with the EHT itself or also with the ng-EHT. Originally, our focus indeed was checking what the EHT itself can do, but what we realized is that a lot of it might be more relevant even for the ng-EHT. So what we did in this work is we were using advection-dominated accretion flow models from Huan and Narayan in 2014. And we've been applying them to a couple of nearby sources, to SEN-A, M84, NGC4594, NGC3998, and NGC4278. And we've been using available spectral data ranging from the radio range to the X-ray frequency to compare them with different model predictions or with different models and to optimize our models to fit the spectra and then to check what are the expected emission profiles and whether we could detect and resolve them with the EHT. These results are published, so they're in the paper below. It's also on AstroPH. So since I will have to be a bit short here, you can find the full information in the paper. Now, why is this useful? I mean, good, some of it might be obvious for the community here, but of course it will give us the potential to look at accretion and also jets at different black hole masses at different distances for different Einstein rings. We'll have different Eddington ratios, and also the absolute physical accretion rate will be different. And of course, this could matter a lot to determine the regime in which accretion happens and to actually explore that. So this just is part of the motivation. The ADAF models themselves that we are using, they're based on Huan and Narayan in 2014. And it's a typical ADAF model, so we assume mass conservation, angular momentum, and linear momentum conservation. There are energy equations both for the protons and the electrons. I mean, these equations include loss processes for the thermal energy. So we include synchrotron emission, Bremsstrahlung, inverse Compton scattering. And what we also included in the computation of the spectra is a simple jet model, where basically we assume a mass loss rate, an electron power law distribution, and a bulk Lorentz factor to estimate the jet emission. Now, our reference case has been M87, since for M87 we had a lot of spectral data, and we've done a comparison and the initial tuning of our models with this case of M87, where in this plot you see both the available observational data, these are the dots here, and you see there's quite a bit of variability in these data because the source itself is variable and data taken at different times show a somewhat different magnitude in flux. And we've been focusing here more on the lower limit when we were comparing to our model predictions. But we developed for M87, it was two models that basically we consider to be roughly consistent with the data. There's some degree of freedom, of course, as you see, but overall it matches quite well. And what we obtain is then a radial emission profile for the source, which can be compared with like the limits of observation for the EHT. You see here one line that indicates the angular resolution. There's another line that indicates the minimum flux that is required for detection. And good in principle to detect the flux, the source has to be here up there in this regime. So the flux must be larger than the minimum flux and the angular resolution above the minimum. And this was our very rough criterion for detection. And obviously, good, we know from the observation now that for M87, there has been a detection now. Even so far we only see the ring. We don't see further information yet. Good, what you see here in our model is the observed emission profile at the different frequencies. You see it for the models. The NT models include a thermal and non-thermal emission. T includes only the thermal emission, but obviously the more relevant case is the one that also includes the non-thermal contribution. Now, we've applied this method to a couple of different cases, and two of the more promising ones are here. So on the left-hand side, you see our result we obtained for CEN-A, where basically the emission profile cannot be fully resolved, but at least the outer part of it could be resolved by the EHT, and also would be above the detection threshold. It's the detection threshold for 8 hours that we show here. Obviously, with the ng-EHT, this wouldn't be even much better, since then the resolution limit would be moving to the left and the detection threshold would be lower. But even with the EHT itself, you could probably resolve some of the emission. And very similar for ngC 3998. I mean, here it's a bit more limited, but part of the outer region you could probably resolve even with the EHT. And it should be improving for the ng-EHT. If we then go to other sources as well, sorry, this table shouldn't be here, we've been looking at ngC 4594. Here it's harder with the EHT, so here with the EHT the source basically would not be resolved, even though the fluxes might be above the minimum for detection. And similar with M84, there would be a resolution problem. But clearly, if we improve this with the ng-EHT, then it's quite likely that these sources could be resolved in the future and that we would be able to get a detection. That's the short summary of our work. And please let us know if you have any questions.
Perfect. Thank you, Dominic. We do have time for a few questions. I can't see everybody on my screen, so if someone has a Boris, go ahead.
Yeah, I'll take one if no one's got one. So Dominic, on this ADAF fit you have you showed earlier, where is the sonic where is the sonic point location in radius? How far from the black hole?
You mean for M87? I mean, this is the case where, we only show the flux profile here. I do not fully recall now out of my head the position of the sonic radius. I see Bedisha, you're here. Do you recall the position of the sonic radius?
No, I don't remember offhand the position of the sonic radius. Yeah.
I mean, we have it in the paper with further information for the sources, so we can certainly clarify that if it's interesting.
Yeah, there's I've seen some work that shows that if your sonic point gets, like in this ADAF model, it can be out at like 20 M or larger. At that point, GR effects start becoming more important than.
You mean when the sonic point is very far away from the black hole?
Yeah.
Okay. At least it was, I believe that it was not my...
We did not include strong GR effects in this case. Like this was a more like a steady state model and not a fully 3D model. So yeah, I want to clarify that we did not include all strong GR effects in this case.
Yeah, that's true. I mean, if we go back to, I didn't show the equations for gravity here, but I think it's an effective Schwarzschild potential that is being used.
Okay, thank you very much. We'll move on to the next talk by Bidisha Bandyopadhyay. I'm sorry if I don't pronounce your name very well.
No, that is fine.
Tell us
Can
about-
you see my screen now?
Yes, go ahead. Yeah, we can hear you and we can see your screen.
Okay, so hello everyone, and thanks for this opportunity for allowing me to speak here. This work is done in collaboration with Christian Fenn, Christos Vorelis from MPIA Heidelberg, and Dominic Schleicher from UDEC. So as a motivation, I would like to discuss some of the points that were raised during the entire conference, that whether the ring-like feature that we see are from the accretion flow or whether it's an indication of the jet base for MAD7. And also we heard in Roger Blandford's talk whether the emission is from a torus accretion or it's a signature of disk wind. And also from Neil Nagar's talk, we know that there is a possibility of better black hole mass measurements for many others agents. And and these sources may have may exhibit different physical scenarios of accretion, winds, jets, etc. So given a GRMHD simulation, there is a lot that goes into post-processing, and two most important factors is like if you have a GRMHD simulation with strong winds and jets, under what conditions are you going to see the ring-like feature or the external winds and jets? And here I typically show the conditions for different black hole masses and accretion rates which are encoded in the Eddington ratios. And as expected, that for higher black hole mass and very low Eddington ratios, which means very low accretion rates, we resolve the innermost structures. Whereas if the accretion rates are high, meaning densities are high and you see a lot of flux and the optical depths are really high, you cannot, resolve features. But if you want to see in our simulations, there is a jet and you want, under what conditions will you see the jet? And such like an intermediate mass, not intermediate, like of the order of 10 to the power of 7 black hole mass and an Eddington ratio of around 10 to the power of -5 may allow us to see a jet. So for this, what we did is we generated some simulations using a resistive version of the HAM code. For reference, you can see the paper by Vorelis of 2019. And so we have different simulations with different magnetic field structures and different floor values, which lead to different kinds of jets and wind structures, and also inflows and outflows. So if we post-process them under typical condition, and if we try to see what happens at different frequencies, we see that for example, in this case, we see the spine BZ jet, and also there is a disk wind, which is more prominent at lower frequencies. In some cases, the spine jet is completely absent, either because like in this case, it's a Schwarzschild black hole, and we don't expect a BZ jet to be launched in that case. And in these cases, the disk winds are so strong that which lead to larger jets, but also the spine jet is not visible because of the strong disk wind. And here you cannot see anything at all. So we then, so this was for we had chosen a black hole mass of around 10 to the power of 7 and intermediate accretion rate of 10 to the power of -4, where we could distinguish these structures, the different wind and jet structures for our simulations. But then we tried to understand what do we see for these simulations if we applied MAD7 like parameters, that is the black hole mass, the Eddington ratio, and the temperature. So we compare all our simulations, and we see that we can see ring-like feature in some of the simulations. And another important thing I wanted to mention, that in all, like if you see this density field, all our simulations have a similar disk feature. So any additional signature that you see in fluxes in these cases where all the post-processing conditions are similar, it is a signature it's a signature of the disk winds and jets. So, and the question is whether whether ng-EHT or EHT can distinguish between such different features, whether they are from the disk wind or whether they are from the jet. And of course, we also vary the disk the R high and R high value is typically done to check the relative temperature between the disk wind and jet. And here is a 180-degree rotation of simulations just to show that, yeah, the fluxes are a signature of the disk winds in many cases. And this is, in this case, like it's the jet. This is a Schwarzschild case where you see the ring and no other feature at all. And of course, these two have such high fluxes from the disk wind that you don't see any feature at all. So I leave as a summary that these models that we have are an alternate thin disk model, which have show strong winds and jets. And for the same model setup, the emission feature depends, I mean, as we just heard in our last talk, that a lot of post-processing and rate tracing parameter, and it's very important to understand what we see and whether for MED7, like with ng-EHT, we can distinguish different scenarios, like whether they are a signature of winds or they are signature of the jet base. So these are the questions. And yeah, with better black hole measurements, can we apply these sources for any of our simulations? We can apply these simulations to any of the sources that we measure in future. Thanks.
Thank you, Vidisha. We do have time for a few questions. I don't see any hands. Okay, so thanks again, Vidisha. We'll move on to the last talk of the session by Kaushik Chatterjee. Kaushik, if you want to share your screen, Kaushik will tell us about tracing the M87 jet with the ng-EHT.
Thank you, Laurent. So, hello everyone. Can you hear me and see my screen?
Perfectly, yes.
Awesome. So today I'll be talking to you about some studies I've done with M87 and its potential link to what we can do with ng-EHT. Now, unfortunately, I'm at a disadvantage here because Andrew and Christian gave some brilliant talks about M87, and it's pretty hard to follow up with that. So I'm slightly modifying the topic to imaging warps and hotspots, so some other interesting features that we can see with some of our simulations. So I recently joined the Black Hole Initiative as a postdoctoral fellow over there, having completed my PhD at University of Amsterdam under the tutelage of Sarah Markov and Sasha Tchaikovskaya, and of course in collaboration with some very, very great collaborators and one pretty awesome master student named Davide. So moving forward with the presentation. So even during this conference, we have seen that M87 has presented us with a lot of information about both the jets as well as the near horizon structure. So such as the EHT papers of 2019. And then again, you have many other radio images at 86, 43, 10 gigahertz and so. I didn't list all of the image or all the very pretty images at radio frequencies here. But one thing more that you can do with these images is you can extract different properties of the jet, such as the Lorentz factor, seen over here in the top right plot, where I'm showing the Lorentz factor on the y-axis versus the projected jet height on the x-axis, and all of the different data points are the Lorentz factors calculated by tracking individual features in the jet. So we have this information, as well as we also have the jet structure, where if you plot the jet radius versus the jet height, you come up with a parabolic structure for over 5 orders of magnitude in distance. So with all the information that we have about M87, we can go forward with our simulations and try to reproduce some of them. So over here, I have a 2D simulation showing the gas density in color, and the black lines over here are the magnetic field lines. So red is the accretion disk, the greenish yellow region is the wind, and the blue region is the jet. So what we'll do over here is we'll match the simulation with the properties of the M87 jet. And we found that the velocity profile matches reasonably well. The shape matched pretty well. And if we kind of look deeper into the simulation, we saw that we had black hole accretion, we had jet launching and acceleration from scratch. And because we were able to resolve instabilities at the jet boundary, we will also get self-consistent jet mass loading and deceleration of the jet, actually. So now, why is this deceleration important? It is important because, like George mentioned to the morning, that you can get entrainment from the wind into the jet, which will increase the baryonic content of the jet, which is actually essential for getting emission out of the jet, and so to observe the limb brightening feature. Now, moving forward from these large-scale 2D simulations, we have to go to 3D to look at, let's say, the features which are more important for EHT as well as ng-EHT, which are the near horizon structure. So over here, we have a very high resolution 3D simulation, and I'm showing you the equatorial plane over here. So we have the black hole, even though it's white cutout over here. And all of these spiral wavelet structures are the gas density spiraling around the black hole. And on the right over here is the consequent, is a resultant ray traced image at 230 gigahertz if you take the simulation to be for M87. And what you see over here, as the gas spirals around, you also see the same type of motion in the image. And because of the high resolution of the simulation, you see a lot of structure in the flow around the image. Now, interestingly, I don't know whether you noticed this or not. During the movie, you see that there are very at one point there will be a flux eruption event. That is, magnetic flux actually escapes away from the black hole, pushes matter aside, and because of that, you see that the image brightness dips quite a bit. Now, this feature is actually better shown if you do, let's say, Sagittarius star at let's say 60 degrees inclination. Is in the same simulation, of course. Now, again, you have a lot of substructure in the image, and when the flux eruption happens, what you begin to notice is that there will be a gap forming between the ring and the outer emission, and the overall flux dips a bit. Now, this is because the flux eruption actually is a result of the formation of a thin current sheet, and this has been referenced before in Bart Riparda and Sasha Filippov's talks yesterday and today morning, respectively, where they talked about the physics of reconnection. Now, additionally, advances can be made on this simulation. Du Su Yoon came out with a paper that included radiative cooling, which turned out to be even important for the low accretion rates of such a star. And Andrew Shell and Christian Form gave us some great talks about what to do with the electron physics in your simulation. Now, moving on, apart from your traditional simulations where you have the black hole kind of sitting in the being parallel to the disk angular momentum vector, you can also have a situation where the disk is tilted with respect to the black hole spin axis. And so looking into high misalignment could be a new frontier that simulations can go into. And a basic question in this sort of setup is, where does a jet point? Well,
1 minute left.
Oh, okay, that one quickly. So needless to say that the jet kind of points at large, in the same direction as the disk and at large distances. And when you ray trace the same simulation, what you figured out is that if you look at a 230 gigahertz image, that you notice that there is a warp in the image with respect to the aligned disk version. And so tracking the time and the spatial variability and at 230 gigahertz will be pretty crucial when comparing between aligned and misaligned simulations. And this could be a great ng-EHT science application. And so we did set forth to look at misaligned simulations using ng-EHT reconstructions, and with the help of Alex Raymond and Daniel Palumbo and the entire ng-EHT team, we were able to see that the black hole shadow size indeed looked different when you incorporated ng-EHT reconstructions as compared to AHT 2017 setup. One last simulation. This is 90 degrees misaligned disk, so kind of like the extreme case that you can look into. And in this case as well, what you will eventually see is that the jet forms, and there will be some amount of precession, and there will be a lot of twisting motion. And this could be something that the ng-EHT could additionally look into to do high cadence monitoring, which could be required to actually look into intermittent jets coming from this sort of setup. Now, on Monday, Elliot Potter gave a very nice talk regarding initial conditions in simulations. And over there as well, we saw that the setups by Sean Ressler also produced these intermittent jets, which would be additionally interesting to ng-EHT. So I think I'm out of time, so I'll just leave it there with the conclusions. Thank you.
Perfect. Thank you, Kaushik. We do have time for one very, very quick question.
Yeah, hi, Kaushik. That looks great. I have one sort of a question about this is whether the radiative transfer you've done here is just using slow light, and have you thought about, or as a fast light, I should say, and have you thought about doing a slow light radiative transfer for your simulations, or is that too difficult with such high resolutions? Thanks.
So yeah, this is indeed all of the ray traced images over here done with fast light. So slow light is difficult just because of the memory budget required, but that is certainly one of our priorities, and we are trying to do slow light, taking into account like how to best make use of the available data set.
I imagine the variable structures you find might look very different due to time delays, for example, if you use slow light.
That could, yeah, that very well could be, especially since at these resolutions you can marginally resolve plasmoids, and so you will get very small scale structures, and these will be very near to the horizon. So yeah, you probably would want to go with slow light in that case.
Thanks.
Okay, thank you. So this brings us to the end of this session. I want to thank all the speakers for the very nice talks. And so now we have about 13 minutes before the start of the next session. It's a coffee break, but if there were a few additional questions about any of the talks during the session, I'd be happy to take them. Boris, you have your hand up.
Yeah, I just wanted to respond quickly to what Brent and Kushik were just talking about there at the end with the slow light. So this done some rudimentary analysis with not like some geometry simulations, and if you just look frame by frame and you try to look at the sort of variability you see, the slow light and fast light, they give different images, not drastically different, but significant enough to make a change. So if you're trying to track some spot moving around, it's very important. But when you try to look for statistical properties like maybe the power spectrum of a light curve or some correlated variability in the image, those tend to be the same. So in a statistical sense, fast light is good enough. But if you try and track specific spots, then I think you need to go to slow light.
Could I quickly respond to that? Okay. Boris, yes, I entirely agree with you. There have been, I think, 2 or 3 studies, and you included, which have actually shown the slow light versus fast light comparison. So I agree that for the statistical analysis, maybe fast light would be okay. But since the main motivation of going to this high resolution is to resolve these plasma structures, which could actually give you flares in the case of such a star, then I think it was Ball et al. 2020, which showed that because if you add in slow light, you could actually have a different flare profile, which would be very, very important for statistics as well, actually.
I have one question for Kaushik.
Go ahead.
So from the standard, let's say, simulations that we do in the ray tracing, we get the correlation time. Now in your tilted models, is the correlation time much shorter because the structure is so different and the evolution is so violent compared to our standard models?
That I haven't looked into this per se. As far as I remember, if you look at the typical timescales for the turbulence, they are on order of the same value, like within 1 order of magnitude. But typically the timescales, I think, are a bit shorter for the tilted simulations.
Okay, thank you.
But not that much different.
All right. Any additional question that someone might have? If not, we should all move back to the main room. Thank you very much again to everybody for attending this session, and to the speakers, especially for 6 very nice talks.
Thank you, Laurent.